So the topic of the conversation today is clean energy business models, policies and legislative support. We'll start with Mr. Rajiv. So why don't you come over and just talk about your thoughts, please. Thank you.
Good afternoon, ladies and gentlemen. Namaskar. I am Rajive Bansal from PETRONAS, Malaysia. So we are here all the way from Malaysia to this far remote place of Goa to share two papers or to share two strategies of Upstream PETRONAS. So as you see, the paper title is we are working on decarbonizing hard to abate combustion emissions via structured methodology of energy landscape assessment. So the two papers that we are sharing today, the first paper is more strategic on how we have strategized to decarbonize our combustion emissions in PETRONAS upstream operations, and with a flavor of a new tool called set pace that we have invented for giving a better efficiency to our machines, or for analyzing where we are inefficient. The second paper will be focused on innovative way of producing GHG free electrons or electricity. So if I want to tell you about the journey of PETRONAS, journey of decarbonization in PETRONAS Malaysia started way back in 1994. We had commissioned our first Baram Delta gas gathering hub somewhere in 1994, where around 100 million scf of the gas which was vented from the oil fields were sent to the shore for utilization. Then we continued our decarbonization efforts with the number of places. If you see, traditionally all the oil fields were hydrocarbon venting fields earlier, and we started converting all those hydrocarbon vents to flares. But we landed in a structured way somewhere in 2012 when PETRONAS announced their first carbon commitments. So that was a first structured approach and a systematic approach which continued, and we reinforced our carbon commitments in 2019, and we are among the first few to announce net zero carbon emissions by 2050 aspiration. If we continue the years, yes, we know there is no carbon tax in Malaysia now, but for our internal assessment purposes, we have a carbon price. Lately, in 2025, we are certified by OGMP in reporting. So this is the journey that we have undergone at PETRONAS as a total corporate, but we have several businesses, and I belong to Upstream. So in 2012, when these PETRONAS carbon commitments were announced, we sat down to check how our emissions look like. So if you can see, in 2013, majority of our emissions were coming from flaring and venting, and only 16% contribution was from combustion. That's where we strategized, and in a decade, we came down by around 78%. So now it's the time to work on the bigger pie, which is the combustion, which is contributing to the highest now. Now, may I like to invite my colleague Azura Aziz, so that she can walk you through the journey of how we are strategizing at PETRONAS on combustion decarbonization on the levers of energy efficiency and electrifications.
Thank you, Mr. Rajiv, for walking through with us the decarbonization journey in PETRONAS. So now I will walk you through the energy landscape assessment that we've conducted for one of our facilities in PETRONAS. As you can see here, the energy landscape is very different for upstream business. It's not like downstream where your energy guzzlers are typically your fired heater or your steam systems. In upstream, as you can see, that majority of the energy, 80 to 90%, actually goes to the gas turbines or turbo machines. So the question is, what do we do with these turbo machines? So this is where we introduce the structured methodology of energy landscape assessment in accordance to ISO 50001, which consists of the 5 steps that you see here. And these 5 steps consist of verifying the fuel gas measurement, identifying excess fuel gas consumption based on the duty required to deliver the mechanical or electrical power, providing a near to real forecast, as well as providing optimization opportunities. And this could not be possible without our in-house digital tool called SETPACE, which stands for Structured Energy Trending Performance Assessment for Combustion Engines. And this tool can be utilized for 4 types of turbo machines, being the gas turbine compressors, gas turbine generators, as well as gas engine driven equipments as well, irrespective of brands. So why was SETPACE created? SETPACE was inherently introduced to us to address the main pain point in upstream. As I mentioned, in upstream, we are working with a very high level of complexity and uncertainty in our operating conditions. Every day we deal with varying flow rates, suction temperatures, pressures, and flow regimes. And even our gas reservoirs, the composition varies from day to day. It makes this very difficult for us to monitor and easily quantify fuel inefficiencies. So the classic example here on the right-hand side is a case for where SETPACE was used to quantify the fuel inefficiency for a gas turbine compressor. So in this chart, you can see that the theoretical fuel gas consumption for this gas turbine compressor is about 3.62 million scarf per day at a gas production of 200 million scarf per day. And right now, my gas turbine is consuming about 3.08 million scarf per day at a gas production of 150 million scarf per day. So naturally, you think that my gas turbine compressor is doing well because when comparing to the data sheet, it's lower. But actually, what SETPACE does is that it uses its thermodynamic algorithms to anticipate what is the fuel gas that it should consume at that particular operating condition. And it turns out I should only be consuming about 2.67 million scarf per day. And now today I'm actually consuming an excess of 0.41 million scarf per day of fuel gas when I could monetize this excess fuel gas to sales. And just to highlight as well that this can be used for turbo machines irrespective of brands as well. So this is our strategy in conducting the energy landscape assessment, and we have developed the combustion decarbonization strategy anchored on our PETRONAS net zero carbon emissions levers of energy efficiency and electrification. So you can see that this strategy is crafted based on the multidiscipline specialists that exist in PETRONAS. For example, the fuel measurement and accounting area is the bread and butter for our metering team to ensure that all the flow meters that are measuring the energy consumption is calibrated properly. And for example, machine efficiency revival as well. It is the core duty of our mechanical and rotating team. The energy demand optimization, for example, is the role of our process team. So this strategy brings essentially all of these people together, showcasing that decarbonization is not a one man's job, not a one department's job, but every specialist discipline is required to be rallied together to achieve the decarbonization agenda. So what did we find in Facility A? So in the measurement and accounting aspect, we saw that there was a 3% of over-reporting of fuel gas. And this is because that we report the fuel gas based on the header flow meter. So the common issue about header flow meter is that the header flow meter typically reads the fuel gas that is going to your non-energy users as well, such as your purge or your pilot, which ends up at the flare reporting. So this scenario is what we call a double accounting, where basically we are accounting for the non-energy users for our energy used for combustion. So fixing this over-reporting, we are able to reduce our GHG emissions by 2.6 kilotons of CO2e annually in reporting. And we've also managed, with SAPPA's ability to provide a near to real forecast, we are able to correct our under forecasting for this facility by 16%, reducing the risk unnecessarily under predicting our GHG emissions. Next is under the machine efficiency revival. To reiterate, Upstream is a highly dynamic and uncertain operating conditions, making it very challenging for us to actually assess the energy efficiency gap in our turbo machines. And SAPPA's is able to do this very systematically. Out of the 6 turbo machines, we observed that 2 exhibit abnormal degradation, the one highlighted in red, the one highlighted in red at 18 and 15% respectively. And these levels are typically exceeding the typical natural non-recoverable degradation that is normally quoted by our manufacturers of the equipment. So the natural degradation is around 6%. So if we are able to revive the machine, whether it is through a water wash or an engine change out or whatever prescriptive plans that are in place for the machine, we are able to reduce our CO2e by 3.5 kilotons of CO2e per year, as well as generate a value of $0.4 million annually by converting the fuel gas savings into sales. Under power generation optimization, we have 2 gas turbine generators at the FPSO operating in a 2+1 configuration. And because of this configuration, they are low loaded at only 40%. And when you low load these machines, they tend to run in an efficient zone where it will consume an excess fuel gas consumption. So the average thermal efficiency of these 2 machines is only at 16%. So what if we, in PETRONAS, change this configuration from a 2+1 to a 1+2? We can significantly increase the loading of this machine to about 80% and improve the thermal efficiency as well, and thereby reducing the GHG emissions by 8.1 kilotons of CO2e per year, as well as a value gain of $1.6 million a year. Another interesting observation that we seen in our facility is one of our gas turbine generators on the wellhead platforms is significantly underloaded at only 23%, resulting in a very low thermal efficiency of 15%. So we in PETRONAS, we look at things not only from the operation point of view, but also from the design perspective. What if I take out this gas turbine generator and put in a smaller capacity, highly efficient gas engine generator? What would the efficiency be for this scenario? So we can see that SAPPA's calculates the GEG efficiency to be about 40% at the power demand of 890 kilowatts, which ultimately consumes 56% lesser fuel gas. And that in turn saves us a 4.9 kilotons of CO2e equivalent per year, as well as generating a value of $0.88 million per year. And last opportunity on the energy demand optimization. In the energy landscape, 10% of this facility's energy is used by fired heaters or boilers at the FPSO for steam generation. At the same time, we have available exhaust heat released through the stacks at very high temperatures at more than 450 centigrades. And the maximum potential heat recovery for this is about 6 megawatts. Actually, we can retire the fired heaters completely for steam generation. And the resultant value, we can reduce the annual GHG reductions by 5.8 kilotons of CO2e and generate a value of $0.7 million per year. To conclude, if all of these opportunities are put together, we can reduce our fuel gas consumption by a big 24%, together with the combustion emissions. Not only that, we are also able to generate value by converting the fuel gas to sales, and as well as addressing our triple bottom line of people, planet, and profit. With that, I end my presentation and happy to receive any questions later. Thank you.
Thank you. Very, very interesting. Let's move to the second presentation. Mr. Wira, if you can come over and do the presentation on waste to watts innovation. Thank you.
Very good afternoon, ladies and gentlemen. It's great to be here in Goa for the India Energy Week. My name is Wira Abadi Sharkawi, and together with the previous two speakers, I am also from PETRONAS' Upstream Carbon Management Division. And today, I will be sharing on the topic of waste to watts. It is about delivering GHG-free electrons by harvesting unused or wasted pressure energy to address hard-to-abate combustion emissions in PETRONAS Upstream. This presentation will cover our journey, the challenges we face, as well as the innovative solutions we are exploring to reduce greenhouse gas emissions. Now, ladies and gentlemen, my previous colleague Rajiv has gone through the pedantics of PETRONAS' decarbonization journey. And as he mentioned, it has been a very eventful past 2 decades as we went through decarbonization within PETRONAS. Now, in PETRONAS Upstream, combustion emissions is the largest contributor to greenhouse gas emissions, accounting for 40% of the total. Offshore gas turbine installations, whether for mechanical or electrical power, typically operate on an open cycle with a system efficiency of 30%, meaning that 70% of the energy is lost. Now today, we from PETRONAS would like to introduce an innovative combustion decarbonization system that harvests wasted pressure to generate power, delivering GHG-free electrons. This slide shows the typical configuration at offshore platforms where high pressure gas is throttled to lower pressure to meet customer requirements. This expansion of gas is an isenthalpic process resulting in a Joule-Thomson effect. Now let's explore the opportunity. What if we could turn these throttled energy losses into electricity using mature, off-the-shelf technologies such as turbo-expanded generators? 2 key factors are needed for this to work: differential pressure and flow rate. Our studies have shown that the higher the flow rate and pressure differential, the greater the output of electrical or mechanical energy. For example, an offshore field producing 150 million standard cubic day of gas with an available DP of 20 bar can potentially generate 2 megawatts of power. We have conducted a pilot study at onshore Terminal A and identified 2 major types of turbo-expanded generators. Type 1 requires preheating of gas and cannot tolerate liquid condensation at the outlet, making it unfeasible due to the additional energy required for preheating. On the other hand, Type 2 can handle mixed phase flows at the outlet without preheating, offering greater operational flexibility and suitability for upstream saturated gas conditions. Now, according to our simulations, the Type 1 turbo-expanded generator can generate 300 kilowatts of GHG-free electrons, but it requires an additional 429 kilowatts for preheating, making it unfeasible. The Type 2 turbo-expanded generator, however, can tolerate up to 30% liquid mass at the outlet and generate approximately 278 kilowatts of power without preheating. Now, circling back to onshore Terminal A, we have approximately 10 bar and a flow rate of 45 million standard cubic feet per day available, which can be harnessed to generate approximately 200 to 250 kilowatts of GHG-free electrons. Additionally, the more efficient isentropic expansion allows for the recovery of high-value condensate, making the economics of this proposal attractive. Now, this project is NPV positive, reduces GHG emissions, and requires much less area to generate a similar amount of power, approximately 240 times less. It presents an innovative way of producing electricity from wasted pressure energy, reducing grid dependency, and delivering electrons without combustion. The more efficient isentropic expansion also allows for the recovery of high-value condensate, contributing to a positive NPV. Now, ladies and gentlemen, in conclusion, this innovative combustion decarbonization system offers a maintenance-friendly, low-energy intensity solution with a significantly smaller footprint compared to conventional systems. It represents a significant step forward in our efforts to reduce greenhouse gas emissions and improve energy efficiency in PETRONAS Upstream. This breakthrough is a testament to our relentless pursuit of new technologies and our commitment to never stop trying in our journey of scouting technologies. So what's next for PETRONAS? We will be exploring potential applications for terminals with high pressure hydrocarbon gas upon arrival and offshore platforms using gas for different petroleum operations. With that, I thank you very much for your attention and we look forward to any questions after the session. Thank you.
Thank you. May I now invite the next speaker, Dr. Peeyush Kumar, on challenges in adoption of coal gasification technologies in India. Sir, over to you.
Good afternoon, everyone. I am Dr. Peeyush Kumar. I am Managing Director of Bharat Coal Gasification and Chemicals Limited, which is the joint venture of Coal India Limited and BHEL. Firstly, I am thankful to the organizers for giving me an opportunity to discuss on coal gasification, which is one of the priority area for coal sector in India. Actually, what is coal gasification? When you talk about energy in India and independence in energy, you cannot think except coal, means because coal is one of the major source of energy in India. More than 50% depends on coal. And with net zero 2070 vision of Government of India, it was thought about to think utilizing coal in a cleaner way. We need to use coal in such a way that CO2 can be captured, which is the only solution for making coal a sustainable manner. In view of this, government thought about making a program of gasifying coal. Initially, it was thought about taking up 100 million ton of coal gasification by 2030. The main aim was to find out what are the bottlenecks in getting it, giving it policy support and facilitating so that the coal gasification can be adopted in the country in a big way. Accordingly, government gave a mandate, and then Coal India Limited had a tie-up with various other Maharatna PSUs, and it came up with 3 coal gasification projects. One is in Odisha, one is in West Bengal, and third is in Maharashtra. In Odisha, it was thought, actually a joint venture was formed between Coal India Limited and BHEL, and that joint venture, BCGCL, is now setting up a project which will produce ammonium nitrate, and ammonium nitrate is a raw material for the explosives which will be utilized in the mining operations across country. Then other 2 projects were basically designed to produce synthetic natural gas, will be substituting the imported gas which is being produced, which is being imported. So in the West Bengal, Coal India has a partnership with GAIL, and in Maharashtra with BPCL an MOU has been signed, and these two companies are now planning to set up a project near Majri in W Skill Command area. So how coal gasification is a cleaner use of coal, I will just like to mention, because mostly coal is used in the boilers, and there are major 5 constraints which are coming up in coal burning. One is that NOx which is produced. So what happens in the gasification? We crush coal with 30 bar of certain pressure along with oxygen and steam. It is gasified. So see, when there is no air in the gasifier, there is no NOx produced, and then when it is again coming out of the gasifier, it is not coming from the chimney, it is passing through the pipes, and which is filtered. So there is no problem of SPM, there is no suspended particles, it is filtered in the process, and then whatever CO is left is converted through the water gas shift reaction, and all CO is converted into CO2, and that CO2 is captured in the rectisol process, partly is utilized for the again feeding coal into the gasifier, and then the CO2, 100% pure CO2 is left with us. So in the CCUS part, carbon capture is almost complete, and only utilization part is to be done, and then the sulfur is removed in the form of elementary sulfur. So all these 5 problems which are coming up in the coal burning in boilers will be taken care in the coal gasification process. So now there are certain challenges. When we thought about that 100 million ton coal will be gasified, we had not thought about that what will be the major issues. People were thinking about that China has adopted coal gasification in a big way, and then we can also follow the same route, we can have the technology, we can gasify coal. But there are certain issues, because in India, the ash percentage in the coal, because of the drift theory of coal formation, inherent ash is much more than across world. In China, most of the gasifiers are working about 8 to 15% ash coal. Even in US, if you go and see, the ash percentage is 8%, 9%, and even if the lignite is further, the moisture is removed, the ash percentage is not going beyond 15%. So this is one of the major challenge which is creating a bottleneck for us to achieve this target. So a number of efforts have been taken up to ensure that we gasify the coal. So I will just go through some of the things that initially we thought about having air products technology for coal gasification. They had excellent technology. In Talcher Fertilizer Limited, they had provided the technology in which pet coke is blended with coal to reduce the ash percentage to a certain level. But what happens in the interim bed technology, the temperature of the gasifier is above the fusion temperature. So the slagging occurs of the ash, and if the ash percentage is quite high, it creates a lot of problem. Then we had also seen number of gasifiers which are working in China. Many are working on interim bed technology, and many are working on fluoride bed technology. And then we had also visited the GTI, where they have U gas and R gas. U gas is nothing but fluoride bed gasification, but they still lack plant running outside China. They claim that some of the plants are running efficiently in China, producing something around 10,000 to 1 lakh Nm³ per hour of gas. And then the TRIG technology, the southern company in US, they tried this technology. They claim that they have operated the plant for about a month, but they have dismantled the plant. So the challenges comes with us is we don't have a reference plant. Before this also, in the fixed bed technology, the Lurgi gasifiers working in successfully in North Dakota. Angul is operating in this technology, fixed bed gasifiers, but the challenges comes when about 50% coal is not utilized because of the screening to be done. That's why there are challenges. And then Thaisanpur Uday had also developed technology, because these technology lack running operating plant across the world. So what happens that in the government sector, when you take a technology, you have to be sure that the technology is running. So this becomes a challenge for us. So problem is that first, in India, the coal quality varies a lot. We have coal available, around 14 to 18% coal at Sonpur Bazari, and we have more than 40% coal available at Mahanadi in Odisha. We have intermediate coal quality available at in CCL in Jharkhand or in WCL in Nagpur. But one technology is not there, means the challenge is there because the variation of the ash in coal is much more. And then we had expression of interest for West Bengal project. A number of technology providers submitted their applications for selecting as a technology licensor. But the issue becomes the lack of the reference plant, because the coal at which our plant is running, that plant is not running somewhere across world. So at present, none of the plant across world is running for ash more than 25%. So we are still in the process. They have designed the gasifiers up to 32% ash. So we are planning to accommodate. There are certain way ahead we have thought about. In R&D also we have limited exposure. Number of efforts have been made in India at IISc Bangalore, at Thermax, at Simfer, in BHEL also. So these efforts are being taken up, but these research institutes requires support from EPC contractors who can now build up the plant, because they have developed around 1 tons per day exhaust, and they wanted to have 100 TPD sort of thing they wanted to develop. Then the capital cost is quite much, so government has come up with a viability gap funding scheme. They have funded some of the projects of Coal India and also in private sector. So again, government is also planning to come up with the second round of viability gap funding scheme. So these things will be taken care of. And about the regulatory uncertainties, some of the things has been taken care by Ministry of Coal, like providing linkage, giving coal at the cost of power, and then also giving some rebate concessions on the additional revenue for the auctions coal block. So ministry is also meeting with various other ministries like fertilizers, petroleum, to find out that the offtake is assured from these projects, so that the private sector makes some interest in taking up these projects. Next thing is that there are certain constraints in these high ash coal. One is the reduced efficiency. What happens that whatever amount of ash is there in our coal, a lot of energy is wasted in heating that ash and again cooling this off. So those energy is lost in this. Then second problem is coming is the increased lagging. What happens, I told you that in the intent bed gasifiers, the temperature is more than the fusion temperature, around 1500 to 1600 temperature. So at that ash melts and it is not uniformly, so somewhere it gets stuck, solidifies. So it creates a lot of problem. And then the oxygen requirement is also quite high. So you require a higher capacity ASU, which increase the cost of generation of syngas. We have created a pathway. There are certain things which we can do to ensure that these challenges are met. One is that R&D focus is there. Government has created a category 3 in which some of the pilot projects and R&D projects will be given support of about 100 crores. So these projects can taken up. Then the proven technology selection criteria, what Coal India has thought about. Recently, Coal India has issued an expression of interest in which we say that the technology provider and EPC contractor can form a joint consortium and they can come up with a solution. Coal India can pay the cost of conversion of coal to syngas, and if there is if they have a confidence on their technology, Coal India will not go into the detail about the existing gasification plant, and if they were to invest, Coal India can give what the conversion cost from coal to syngas. So these are the things that evolving to ensure that some new projects are coming up soon. What I wanted to say that coal is the major source of energy in India, and the time has come that coal should be utilized in a cleaner way. Cleaner way means coal gasification, and coal gasification, there is a need. It will take about 4 to 5 years. It is a transition time in which slowly from burning of coal, we will be coming to gasification of coal. So the path forward I had already discussed. We are going ahead with the R&D. We are going ahead with the proven technology suppliers who wanted to invest, not making a criteria for them to show that they have a reference plant, and then there is a supporting policies. Government is also coming up with a second round of viability gap funding, about 50,000 crores. So I hope that with these supports, some new projects will come up on gasification. Thank you. If you have anything, you can mail to me at md.bcgcl@coalindia.in. Thank you.
Thank you. Thank you, sir. I think it was very good. May I call the last speaker, Mr. Aravind Babu, please, on the stage to talk about optimal resource mix for Indian power sector decarbonization. Thank you.
So, good evening, everyone. Myself, Aravinda Chinnu. Today, I'm going to present on the topic optimal resource mix for Indian power sector decarbonization. So, to determine the optimal resource mix, we need something called a capacity expansion model, which takes in a number of input parameters and results in a number of outputs. And this study is not the first one. Several studies have already assessed the resource mix for different time periods. And we can see that for solar PV requirements, it goes up to 6,000 gigawatt by 2070, and for wind, it goes up to 2,500 gigawatt by 2070. So these numbers are staggering, and one thing we can understand is we need to be very critical about the input data that we feed into the model. So two things I want to point out in this presentation is the hourly demand data that is used and the capacity factors of solar PV and wind. What usually happens is studies generally assume that the capacity factors of solar PV and to remain constant in the future periods as well. And while estimating the electricity demand, they do not account for the emerging demand drivers like EV charging and additional cooling demand due to climate change. So we'll go by one. First is the capacity factor for solar PV and wind. So to determine the generation potential or the capacity factor, we need to obtain the climate data from the same basic climate models, and we obtain for two different scenarios, SSP 245 and SSP 585 scenarios, and for three different weather parameters: temperature, wind speed, and irradiance. And we did this for a future period 2070, and we compared with present 2000. And we did this for all the grid points that is mapping over India at 1 degree north and 1 degree east differences. And for estimating the solar generation potential, we need two things, that is the total irradiance incident on the panel and the efficiency of the panel as well. And for wind generation, we assume that the wind generation is going to be proportional to the cube of wind speed. So just a brief look at the methods used. So the total irradiance incident on the panel, it depends on the two components of the solar irradiance, that is direct normal and diffuse horizontal. But since climate models doesn't have data for the components of solar irradiance, we assume the solar panel is going to lie flat horizontal on the ground. So the total irradiance on the incident on the panel is nothing but the global horizontal irradiance, which can be obtained from the climate models. And the next thing is the panel efficiency. It's a function of weather parameters, temperature, irradiance, and the wind speed. And this data again we can get it from the climate models. For wind, again, the total generation is going to be a function of hourly wind speed. But again, the problem here is the climate models doesn't provide data on hourly wind speed. So we assume that wind speed to follow a two parameter variable distribution of K and lambda. So K is going to be the shape factor, and lambda is a function of mean daily wind speed and the K itself. So mean daily wind speed we have from climate models, and the shape factor we estimated from the Mera2 data. Again, the thing is, the data provided is at 10 meters, right? And we need to extrapolate to 1 or 2 meters, which is corresponding to the global average height. So when you look at the results, we find that the solar generation potential is going to decline in every location with respect to 2000 for under both the scenarios. But one thing shows is under SSP 245, we can see only minor region shows a variation greater than 2.5%. But again, for 585, you can see the variation goes more than 2.5 in many locations. The next thing, we can see the generation potential for wind. We can see when compared to the solar PV, the variations are much significant here. So we saw around 0 to 5% variation in solar PV, but for wind, we can see it's from minus 20% to plus 30%. And again, many locations show an increase here, which was not seen in solar PV. And under SSP 585 scenario, we can see the increase is much more pronounced. It goes more than 20% in certain locations in India. So moving on to the second part of the presentation, the demand estimation itself. So it involves collecting the demand data, which involves electricity demand, weather parameters, GDP data, the temporal features. And the first process is to clean the data, to remove the outliers, to split the data into training set and testing set. The training set is used to train the model, and the testing set is used to analyze the model performance. So using the train model and the future weather parameters and projected GDP data, we can get the total future electricity demand. But this doesn't account for the emerging demands like EV charging and increased cooling demand due to climate change. So those has to be separately assessed and to be added to get the total electricity demand. So to assess the additional cooling demand, the thing is cooling energy increases due to two things. One is the number of ACs installed and the change in weather condition itself. So we assume the number of ACs to grow proportional to the GDP. So this component is already captured in the base demand. The next thing is to assess the cooling demand change with respect to the change in ambient weather conditions. So for that, we estimate something called CDDs, that is cooling degree days, for the three most popular cities for 2070 and the present period. But increasing CDDs doesn't necessarily say that there's going to be an increase in cooling energy. So we need to obtain the correlation between CDDs and cooling energy. So for this, my previous paper was used, where we see that for every climate zone, there's almost a linear correlation between the CDDs and cooling energies. So using these correlations, we can obtain the actual percentage increase in cooling energy and finally incorporate them into the already calculated base demand. So EV charging, we need two things. One is to estimate the number of EVs itself, and finally to estimate the total charging for each of the EVs. So for estimating number of EVs, we assume the on-load vehicles to follow a lag compressed curve. And by 2070, we assume all the vehicles to be electric vehicle. And we can obtain the survival rates itself from the previous study. So this table shows the efficiency, average kilometer travel, and the ratio of vehicles charged for all the 2, 3-wheelers and 4-wheelers. And using this, we can estimate the total EV charging demand and finally incorporate into the already estimated GDP-based demand. So how does the demand for 2070 look like? So the total demand is going to vary between something around 6,900 to 7,550 terawatt. So which is around a difference of 650 terawatt hour. So put it into perspective, the current demand, it's around 1,600 terawatt hour. So if you miss out on the emerging demand trends, we are going to miss out about 50% of the current demand. And the second thing is the EV demand is going to be much higher than the additional cooling demand. Under SSP 585 scenario, you can see that the demand is almost twice of SSP 245. So now that we have estimated the input parameters, we have the hourly demand data and the capacity factors of solar PV wind, we can input this into the capacity expansion model to look at the optimal resource mix. So other input parameters include the technical and financial parameters of different generation and storage systems that we can obtain from CE and NREL ATB. And the network transmission network topology, we assume that there is 5 regional grids. And the limits on the generation and storage capacity is based on the renewable potential, and we assume there's going to be no new fossil fuel plants other than that's going to be planned on under construction. So this table highlights the potential limits for solar PV, wind, biomass, and hydro, and the conventional that we assume in the study. So when you look at the feasibility, whether we are able to match the demand in 2070, so we got around 60 scenarios. We have 2 different climate scenarios. We have 3 EVs where we have slow, medium, and fast adoption scenarios. and wind turbine height itself from 120 and 150 meters, and we limit the nuclear installed capacity to be around 100 gigawatt, and transmission capacity we vary from 1x to 5x of the present capacity. And we found that it's infeasible under 45 out of 60 scenarios that we are not able to meet the demand of 2070. It is feasible only under the SSP 245 and the hub height of 150 meters. So this is important because at the hub height of 150 meters we have higher potential and we have higher capacity factor as well. Suppose if we increase the nuclear capacity to be around 127 gigawatt, the feasibility increases it even under the SSP 585 scenario, but again under the hub height of 150 meters only. So one important thing I want to point here is, like, even if we fully explore the renewable potential, so the decarbonization of power sector is still not going to be achievable. So how does the resource mix actually look like? This is for the scenario SP245 and we have a height of 150 meters. So we can see that the entire solar PV potential is used up in all the regions except the northeast. And wind as well, we are going to use up all the potential except for the south. And wind capacity requirements are highest in south, followed by the west and the north. And battery requirements are going to exceed more than 1 terawatt hour in 3 of the regions, that is north, west and south. So naturally the question comes, if we increase the transmission capacity, what's going to happen? Like, are we going to see any differences in the optimal mix? I think it is like, even if we increase from 1x to 5x, we can see that wind and solar PV are going to show very little variation, and it's going to remain very close to their potential limits. However, the battery storage requirements are going to decline by around 0.2 terawatt hour. So one thing here is the increasing transmission capacity, it helps to reduce the storage needs, but a further increase has negligible effect. So again, the question comes out, so what if we relax the limits for renewables? What if we say we have more than 10% of wasteland to build the renewables, and what if we use rooftop solar as well? So here all the limits are relaxed, and we can see when the limits are relaxed, the dependence on solar PV and battery actually increases, while the wind, it actually decreases. And for south and north, we can see very high levels of solar PV, and this again necessitates very high levels of battery requirements. So in conclusion, the key takeaways are we need to incorporate this climate change impacts on the estimation of capacity factor, because for solar PV we see 0 to 5%, and for wind we see a significant variation around minus 20% to 30%. And we need to account for these emerging trends in electricity demand, because it's going to be crucial, because the variation is around 650 terawatt hour, which is off of the present demand. And conventional power plants are going to still play a major role in the future resource mix, as identified renewable potential is going to be insufficient to meet the projected demand. And investment in transmission sector is going to be crucial, as the battery requirements can be reduced, but beyond a certain point, it's going to provide only a limited benefit. And finally, the firm sources like biomass and nuclear are going to play a critical role in this power sector transition, because the solar PV and wind has a heavy dependence on the storage systems. So the future work will therefore us to look at the multi-year optimal mix to develop a long-term decarbonization roadmap. And we need to include the cost uncertainties while modeling a stochastic framework. And we need to evaluate the reliability, including the frequency, stability, and reserve requirements. I would like to acknowledge my supervisors, Professor Venkata Sailanathan and Professor Rangan Banerjee. Finally, I'm thankful to Sri Narasimhan, the former CMD of Great India, Sri Vivek Pandey, General Manager Great India, for their timely support. So I'd like to end my presentation here. Thank you.
Thank you. Thanks, everyone.